So, call is now being recorded. And since I'm not representing my company in this talk, so I'm not supposed to use the company name or logo anywhere. So that's why I requested specifically not to put my company name in any of the flyers that went around. So this is basically what we are going to cover today. I hope, yeah. Okay. Anyways, I've joined from two devices, so I can see what is slides are changing or not. So initially, we'll look into what is basically a smartphone, uh, what is inside a smartphone. We'll try to dig deeper into a phone and figure out how the entire system is organized and how close it is to the embedded systems that you actually work in the RoboClub. How the same concepts at a little deeper level are applied to build bigger embedded systems like a mobile phone or even bigger appliances. So we'll try to connect that in the first part of the session. Probably that will take some 15 to 20 minutes. And then in the second half of the session, all the topics are related. So we'll basically see how the mobile technologies have evolved over the time, starting from 1G, which you might not have heard. And then today we are talking about 5G. So we'll just glance through that. What are the different technologies when they came? What are the fundamental differences? And then we'll talk about, since we have already covered the smartphone architecture in the first topic, we'll also cover what are the different components of a mobile system, a mobile network, and how does all those components work together to make your call or a data session active on your phone. So we'll try to study the mobile network architecture. Then we'll come to mobile communication protocol stack. Basically, uh, for people who are into third and final year, just like you have studied computer networks where you have a TCP/IP stack, similarly we'll have a mobile communication stack for each of the technologies, and then we'll try to explain what are different layers, what do they do, uh, and then we'll also talk about what are the international bodies that are actually making these standards, because if there are no standard regulations across the globe and every operator and every mobile manufacturer starts making their own systems, then it's going to be a mess, because one phone manufactured for one network is not going to work on the another network. So that's why we have standard international regulations, international standards. So we'll look into what are the bodies that are making the standards. Finally, in the sixth topic, if time permits, I'll just give you an overview of what 5G is all about, how it is different from 4G. Then we'll also touch upon two new topics that is called V2X and MEC, because these are the areas where you can even build your own BTech projects or MTech projects. You can even work while within the college, make some useful projects out of it. So that's why I'm just going to give you an overview. I'm pretty sure the time will not permit me to talk in detail about it. Uh, in case you want to have a detailed session, probably V2X or at least MEC and 5G, we can definitely have a detailed session sometime in future. So that is the agenda for today. Again, as I said, at any point of time you have a question, please feel free to interrupt me and ask your question. So again, about me, I've already briefed, so let's not spend time on this. So the first thing that I would like you people to buzz on the chat. You know what's you know what is a phone, but what do you think that what all components are there inside a phone, or what does a phone have? So the chat is open. Please buzz your inputs on the chat. I'm just monitoring. So what all you think that a phone has? Anything that you feel that that is inside a phone? Please type one by one, or two or three components together. Maz, I'll come to your question later. So we have started getting responses. Vidita says a processor. Tavish says GPS. Priyanka says PCB. Yes, very much correct. Looking for more answers. GSM module. Okay. Sensors. Very good. Battery, camera, processor, modem, sensors. Okay. Very good. I'm surprised people are missing one very fundamental component. Chips, integrated circuits, very good, Swalia. No, these are generic things. So in detail, rather two very fundamental things you people are missing. Think about it. Just like a television, a board inside mobile device to audio and transmitter and video outputs, a processor to antenna. Yes, Avid, that's what I was looking for. SIM slot, very good. Torch. Guys, don't you have a screen on the phone? You're talking about chips and RF and this. The first thing that you pick up a phone is your screen. And that is when it breaks, you spend half of the cost to replace it. Exactly. I think Apurva keep. Sorry, am I spelling your pronouncing your name correctly? It's Apurv or Apurva? Okay, we have a RAM. Yes. Uh, so most of you have guessed it right, but most of people said that there's a processor. Fundamentally, if you look into a phone, if I talk about a smartphone, so there are essentially three processors in a phone. So that is what I'm going to talk about in the next section. Like all the components that you have talked about, how are they organized in a phone, who controls them, and eventually how the entire system works. And then I'll look into the software architecture of the same. So and I'll also give you the technical terminologies that are used for identifying those things. So as I said, there are three processors on a phone. So the first one is called an application processor, or AP in short. The second one is called a baseband processor, or then it is called as BP or CP in terminology. And then the third one is an RFIC. So before I go into the details of this, can you guys buzz me, like when you buy a phone, what all things you look or look on the box or specs into it? When you think that you want to buy this phone or that phone, what all the things that you consider? RAM, yes, very good. Don't you guys look into what the processor is, whether it's Exynos, it's Snapdragon, or like there are hundreds of it. And then when you say that you it has a RAM, or you look for the RAM, do you know which RAM are you looking at? You can always unmute yourself and then speak up. So in the interest of time, I'll just be proceeding a little quickly. So as I said, fundamentally, there are three processors in a phone: the AP or application processor, BP or the baseband processor, and RFIC. So application processor is the main processor that in a phone, that is on which your operating system, be it Android, be it iOS, be it Windows, be it Symbian or whatever, is running. So that is the most powerful processor. And whenever any phone advertises about it, that this processor is a 2 gigahertz, this phone has a 2 gigahertz processor, or a 1.5 gigahertz processor, or quad core, octa core, and so on, they are always talking about the application processor, because this is a processor that is talking literally about that takes care of everything that you do on a phone, whether you talk, whether you play a game, or you do some browsing, or you do something, or you use Wi-Fi, or you use navigation, or literally anything. Then baseband processor is basically your modem. Technically, it's called a modem that only knows how to talk to the network, mobile network. It usually doesn't have any GPS, it doesn't have any Wi-Fi, it doesn't have any Bluetooth. So it only takes care about talking to the wireless cellular networks. Because as we'll see in the next couple of slides, that talking to the network is itself a big challenge in itself. And all these technologies that we talk about, 1G, 2G, 3G, 4G, and so on, they are taken care by this baseband processor. And finally, the third thing is an RFIC. So again, a baseband processor has a lot of things to do other than, and it is too much occupied to control the antenna and do the actual transmission. Because these days we do talk a lot about a digital communication, but one thumb rule that everyone needs to understand is, no matter how advanced we get into communication technologies, the final transmission on the air is never going to change from analog. So all those things, like whether all the data we take, all the audio packets we take, everything is digitized by the application processor, baseband processor. But finally, when it is going to be transmitted by antenna, it has to be an analog signal. So RFIC basically takes care all the digital data from your application processor, then baseband processor, and finally converts it or modulates it, as it's a technical term. So it is finally modulated on an analog carrier and then finally transmitted it. So RFIC takes care of your modulation, demodulation, and then controlling all the antennas that are present on your phone and finally transmitting it to the mobile network. So RFIC doesn't understand what is 0 and what is 1. It only knows that there's something as 1, something as 0, and I need to transmit it. Or when the network is transmitting it to me, I need to receive it and give it to a baseband processor. For it, every 0 and every 1 is same. It cannot figure out whether you're trying to power on the phone with that 0 and 1, you are going to power off, you're making an audio call, you are going to use data, or you are going to play PUBG or anything. It doesn't literally know. All it knows is just transmit zeros and 1 over the network. That's all. So this is the crude architecture. Then if we talk about all the components that you people have been talking about, before we go to the components, so RAM, again, each processor is associated with its own RAM. Application processor has its own RAM that is shown on the top, and then baseband processor has its own RAM that is shown in blue. Again, when you buy a phone and you talk about the RAM, you're always talking about the RAM in orange that we have shown, because that is the key RAM that is going to help the AP in processing any application that you run. Finally, because it's any processor needs a memory, so there's a small RAM associated with the CP also, but usually in the specifications of a phone, nobody talks about it. Because this RAM is adapted to the capacity of your processor as well as what all technology is supported. Finally, coming on to the operating system, so Android or iOS or any other, and all the applications that you install are running on AP, as I said, and then all the components that you have listed. So most of you got it, like you have a display, keypad, camera, sensors, battery, power management, memory, then USB, NFC, Bluetooth, Wi-Fi, GPS, I forgot to write. So all these components are controlled by the application processor. They are connected to it. There might be separate drivers, just like for people working on embedded systems in RoboClub, you might put a motor driver before the microprocessor and the motor. You might put an analog to digital converter separately. You might put certain additional ICs on the your PCB, but the core decisions are taken by microcontrollers. So similarly, all the processing control is with AP, but there might be separate drivers for each. Like for example, camera is getting complex now these days with 40 megapixel camera and so on, and so many features coming onto it. Every camera may have its own imaging sensor or imaging driver, but the control again rests with AP. Similarly, Wi-Fi is a complete protocol. So usually you have a separate Wi-Fi chip on the phone, but that will take care of implementing the Wi-Fi standards. But again, that is controlled by the application processor and so on. So Bluetooth chip might be there. NFC has a separate chip. Your memory, when we say memory, we talk about all the flash memory, we talk about SD cards, internal and external, as well as the inbuilt ROM. So all those memories are controlled by this thing. Sensors, as we talked about, the sensors may have their own drivers, but again, they are controlled by application processor. Speaker and microphone, from where when you make a call, you hear the audio or you speak and the audio packets are captured. They are essentially associated with application processors, but in some phone designs, because when you talk about speakers and microphone, there's something called as a DSP involved, digital signal processing. Or immediately the packets have to be converted from analog audio that you're speaking to digital format. So usually the DSP chip is associated with CP or baseband processor. That is why they also are connected with a baseband processor. But again, this depends upon different manufacturers may have a different design of connecting this directly to AP or CP as a design maybe. And finally, there is one form of communication between the two processors. So again, students from computer science or people who have studied computer architecture, you must have studied different form of interprocessor communications, right? You may have a shared memory, you have the PCI bus or UART interface or different USB interface. So the yellow arrow that you see over there is basically one form of interprocessor communication. So that is how the two processes are communicating. Similarly, there is one similar interprocessor communication happening between BP and RFIC, but this is not as rigid as this, because the entire design of the phone and the performance, like how much data throughput you will get, how much data speed you will get, will depend upon how strong and how robust is this interface. Because the amount of data flowing here is much more than flowing here, because here you also have a lot of control messages that are flowing. We'll talk about it in the later terms. So this is all about AP. Finally, the only prominent component that CP has is an external SIM card, as well as the prominent component with the RFIC is the antenna. So this is how your entire phone is organized, and a lot of effort goes into designing, placing these things, because now people from electronics will study a course on antenna design, I think in third year or final year. So you would be surprised to know that the size of the antenna depends upon what frequency of communication you are using. So if you are using very low frequencies, your size of antenna grows big. And then with the evolution of antenna, there are multiple types of antenna that have been introduced. If you remember, earlier phones used to have that spike sort of antenna coming out of it. Now, with the advancements in antenna technology, people have been able to replace those antennas with something that is hidden inside the phone by this form of a microstrip antenna, which is as good as like a cable flowing across your phone. So again, the placement of that antenna plays a very crucial role, because these antennas are so sensitive that if you hold the phone in one way, like if you hold the phone with your left hand, or if you hold the phone with the right hand, you are going to cover a certain portion of the antenna, and that basically is impacting the amount of power that can be transmitted by the phone to the network, or the power amount of power that can be received. So with that changes, all your internet speeds and audio qualities are going to change. So placement of these components on the phone, whether one component is going to sit on top, on the left, on the right, is very crucial. So that is, I mean, when we design a simple PCB in a RoboClub or any embedded system, the only consideration we take is no two wires should touch. But when you design such complex systems, or when you go with such higher scales of integration, you need to take care of all these things also. So any questions on this slide before I move ahead? Fine. So this is just a small slide showing how does the RF circuit work. So as I told you that no form of communication in the world is truly digital when it's getting transmitted. So you can see that you have a modem baseband processor which is having all the digital data, but when it finally comes to the RFIC or RF transceiver, it is all the digital data is finally modulated onto analog carrier that you can see at the bottom of the slide, and finally it is getting power amplified. You have filters, you have switches, you have LNAs, and so that when you transmit your signal, there's minimum amount of noise, and then finally it goes into a duplexer circuit, diversity, and then antenna tuner, and finally it's getting transmitted by antenna. I'm not going to talk in detail about these components, because they are something very specific to electronics engineering, and then that too you will be able to appreciate only when you have studied at least that topics until final year. So one thing that I would like to emphasize here, that people feel that what you study in the college is not used. But again, I would like to reiterate that every subject, literally every subject that you study, has an application somewhere or the other. You may not be directly using it, but if you don't know that subject, you might not be able to understand something fundamental uh, as an advanced topic. So all these things, if you talk about, they are taught in the second year of electronics engineering in a course called analog devices or analog circuit design. You might be studying how to make an amplifier, how to make a duplexer, how to make a diversity switch, and so on. So do focus, and all these modulations, demodulations that you will be studying in your second year and third year of courses. So do understand them thoroughly, both for electronics and computer science students. Communication is a very fundamental course. Do take that seriously. So that is how your signals are getting transmitted. And then again, as I said, there are two fundamental processors on the phone. There's a lot of competition in the market. I've listed down some of the key players who are manufacturing these processors or the chipsets as they call. So one thing that we need to know here is in the design, I told you that there are two separate processors, but there might be two different cores I mean, everything might be put on a single chip or a single SoC, which are complex embedded chips. So it's not necessary that every phone will have two physical processors, but they might be different cores or different. I mean, everything might be put on a single SoC. So here are a couple of key players. Like if you talk about AP, Qualcomm is one of the biggest manufacturers, and their chipsets fall into the family of Snapdragon. They are the latest ones. Earlier they had MSM series and so on. Then if you talk about Samsung, you have a Exynos processor that is usually put into Samsung phones. You have NVIDIA Tegra series. Intel is manufacturing its own application processors. Then you have Kirin, and then obviously Apple has its own A series processors. So these are the key players in the application processor market. If you talk about CP, this is something very specific to mobile communication, mobile protocols. So you have core mobile companies here. Qualcomm is one of the key players. Intel, the mobility division is now being acquired by Apple. So it's like Intel Mobility or Apple, I don't know what they call it. Samsung is there, MediaTek is there, Broadcom, sorry, I forgot to put Marvel. And then there were a couple of other companies that are no more existing, so I'm not trying to put their names now. So if you want to go into like either into core embedded systems or core communication, mobile communication things, so these are the companies that probably you should be targeting. And to get into this, you need to have very fundamental, good fundamentals of your operating system, of how communication systems work, of your circuit design, your digital analog concepts. So these are things that you should be very clear on your thing. So coming on to the software side, this was the hardware component. Now, if you look into software, because any hardware cannot work without a software, right? So first we'll look how the application software is organized. I've taken a typical example of an Android uh, OS, and then we'll take a generic example. So anything that, since you know that Android is built up on a Linux kernel, so uh, at the bottom of the OS stack is a Linux kernel, which will provide you all the drivers or the hardware abstraction layer to talk with the processor. And then on top of the kernel, since the kernel provides APIs to different libraries, there are different libraries to talk to the camera, to talk to I mean screen, to the GPS and everything. So that Android provides inbuilt libraries that can be used, and then there are application framework components which can be used for different events, for different you can say different functionality using, because you may need not to implement everything. For example, you want to make an app and you want to probably play a music. You just need to tell Android that this is a music file is stored on this memory, and you go and play it. You need not know how to make the speaker run. So that is a functionality that probably framework and the libraries provide you. And finally, when you make applications, all your apps that you talk about are sitting on the top layer. So this is how a complete operating system is organized. So again, when you go into the market and you want to I mean get a job in any of these layers, so each layer has a different requirement. So you should be very clear whether you want to make an application, you want to become an app developer, or you want to go into the core kernel stuff, or you want to go into the Linux kernel or the driver layer. So whatever we are working in RoboClub, you write basic codes to talk to motors, to ADCs, to wireless components, or probably you are already working at the bottommost layer of which I mean, there's something called as the driver layer, basically. So all these things you are writing right now. You when you interface a keypad, you write the code for every button that you're going to press, right? So that is basically your keypad driver. But when you make an Android application, I mean, for those people who have already made applications, do you really care that how the key is pressed? All you get is when a key is pressed, the Android framework application framework is going to give you a event. but how that event is generated, and first of all, how that key pair is recognized, and then how that event is generated. So all those things happen in different layers. So if you want to become an app developer, you need not know all this stuff. You should be very good at your Java and C++ programming languages. This area is mainly for people who love programming or applications. Then you should also be able to understand at least what all functionalities are provided to you by the OS, be it Android, be it iOS, and so on. So unless until you know the API framework very well, you will not be able to develop your applications. So for app developers, you should be very good at your programming concepts, especially Java and C++. You should know how to use SDKs of Android or iOS. I'm talking about only about these two operating systems because they are the most prominent ones. And then you should also be aware a little bit of libraries. But then if you want to go into OS development, which is a little more tricky job, so you should be able to have very good concepts in operating systems courses that you have, how memory management works, how all those things work. And then only you can be able to make all these libraries, because these libraries provide an implementation of the core concept. For example, a browser. When you make a web-based application, all you need to know is how to open a socket. But how actually that socket is getting opened, and how that data is actually getting transferred from AP to CP, you don't care at application layer. But if you want to develop a library, or you want to go into these layers, you should have a very good understanding of how the basically your network components are working, how your memory management is working, how your power management is working, and so on. Again, I'm not working in these layers, so I just have an overview. In case you want a detailed session, probably we will have more experts coming onto this. And then core libraries, and these things are basically runtime libraries that you get integrated. And finally, the kernel part, I already explained that these are the core drivers that are required to talk to different hardware components. Now, why this is needed is because Android is not going to change. For example, you have one phone from Samsung, one phone from, say, for example, LG, one phone from OnePlus. Now, all these phones are going to have different camera from different manufacturers, because nobody manufactures camera. So now if Android is going to release different versions for camera A, camera B, and camera C, there will be a hell lot of versions for what do you call cameras, or a hell lot of versions of Android, and it will be very difficult for Google and for any vendor to maintain it. So that is why there's something called a driver. So driver is basically provided to you either by the phone who makes the phone, or by the person who makes a camera. So the maker of the camera knows his camera, and then he will provide a driver that can work with Android. So all Android needs to do is basically pull up that driver, and then whenever it wants to switch on that camera, the driver will provide you a functionality or a function, let's say, to open the camera. All you need to do is call that function start camera, and the camera will be started. So what actual assembly commands to send, or what hardware level commands to be sent to the camera, what all signals are to be activated, all those components are taken care by the driver layer. So I think this you will be able to understand better, because you are already doing as a part of RoboClub. So when you want to do any thing, and if you are not doing it, basically many a times you include libraries like timer.h, you include basically ur.h, or you include adc.h. So all those basically are providing you a driver layer functionality. So this is basically an overview of the AP software. Again, I pause here for questions. I'm not getting a lot of questions, so that means people are not getting it. It's going over your head. Am I going too fast, too slow? Please speak up.
Yeah, maybe a little slower will be helpful. I have just joined, but I'm following it. Thanks.
Okay, yeah, good to hear. Other people, somebody from second year, third year, at least you should by now you should have some questions. Because till now what I've talked about is something that you keep hearing. Now the next slide is something that you might not have heard until now. Guys, no questions. Come on.
So, good evening, guys.
Yeah, good evening.
Actually, there's a question. So there's a Exynos and Snapdragon Industries. So like I want to know what is the basic difference between them, and if I want to enter this processor industries like in manufacturing them, what type of projects or what kind of studies should I be doing? Because uh, जो भी हमारे यहाँ स्टडीज होती है वो आईसी से रिलेटेड वो ज़्यादा डीप नॉलेज में नहीं है जैसे there's large scale integration and different other integration schemes. So we don't know much about it. So what type of studies that I will be doing if I want to work in that?
Okay, that's a very good question. May I know your name and branch?
My name is Ritik Sharma and I'm second year electronics engineering student.
Okay, so your first part of the question is what is the difference? So fundamentally, there are two different products from two different companies. Snapdragon is from Qualcomm, Exynos is from Samsung. So this is just a family. Exynos and Snapdragon are not specific processors. Within Snapdragon, you will have 845, 855, 850, 835, 700, and 600, and so on. Similarly, Exynos will have a lot of products. So they are, first of all, they have a family of processors, not an individual processor. And then based upon what processor you are picking up, say for example, 835, if I remember, doesn't support 5G. Whereas 850 supports 5G. Similarly, in Exynos, some processor may be supporting a lesser RAM, some may be faster, some may be slower. So that is the fundamental difference. But you cannot say that Snapdragon versus Exynos, what is the difference? That is very difficult to understand. You should always compare a specific processor from the Snapdragon family and a specific processor from the Exynos family. Then only you can draw a difference. So that I hope that answers the first part of your question. For second part, there are multiple things. If you just want to design a processor, if you want to enter into the processor design industry, you will need to be very good at your digital concepts of digital electronics, digital logic, and then your IC design. So digital logic, when I was there, it was covered in second year. I'm not sure if there has been a change in the curriculum. Digital IC design is covered in fourth year. Analog IC design is covered in seventh semester, and digital system design is offered as an elective that was taken care by Hassan sir when I was there. So for that, you need to be, as I said, you need to be very good at your digital electronics concepts, and then you have to learn certain softwares like Verilog, VHDL, or any other software that is more prominent in the industry right now. So, but then apart from that, you should also be very good at your operating system concepts. So unless until you're good at operating system concept, you may not be able to do a lot of the other part of the processor design that happens. So Abid, would you like to add something to this?
Yeah, so I am from the processor industry. I work at Marvel, and we'll try to see if we can have a follow-up session, probably in the next session on processor design, as well as get somebody from Intel. So one thing which I would like to add is, like, every year from AMU, even B.Tech as well as M.Tech, they go to some of the best companies. So right now, I think in the last 5 batches, I know of people who are working in Qualcomm, Intel, NVIDIA, Marvel, all who have passed out from AMU. So there is good enough foundation that is built by the electronics department for these industries. So I think whatever is the courses that you learn till 4th year, right? Especially you have a digital design course, you have a VHDL Verilog course. Those will be helpful for you, and I think those should be sufficient for you to gain a foothold in the industry. So we'll try to cover up as a separate session, probably in the next session.
Yeah, and by the way, these courses are available to computer science students as well. It's not like just exclusive for electronics. Other than digital IC design and analog IC design, where they talk about bus placement. Other than that, everything is also available to computer science students.
Yes, I was from CS and I have studied these courses. So yeah,
I think. Yeah, hi, I'm Shakir actually. So I think to exactly answer the question that what do you need for chip design to enter the chip design industry, I think all the relevant coursework is already there. One coursework I think, which at least I do not see right now in the curriculum, is the computer architecture course. That is, I think there are a lot of online courses which are pretty good. So if you want to have a good like sort of working knowledge of how does a MIPS processor or general processor works, like 5-stage pipeline or 3-stage pipeline ones. So for that, I think that is one additional course that you can voluntarily pick up. Otherwise, I think basic from BJT, from MOSFET level, device physics to digital gates, entire coursework is covered throughout the 4-year course.
Yes, somebody wanted to come in.
Oh, thank you, Bhai. Actually, there's one extra question that during the interviews that you will have to go through for these, आपको अगर जॉब चाहिए तो उसके लिए तो मतलब जितना भी कोर्स से रिलेटेड है वही सब वो इंटरव्यूज में आस्क करते हैं आपसे.
More or less, उनके एप्लीकेशंस लाइक अगर कोई भी कोर्स है तो उस थ्योरी का एप्लीकेशन एक सिंपल प्रॉब्लम दी जाएगी वेयर यू हैव टू अप्लाई दैट थ्योरी एंड देन सॉल्व द प्रॉब्लम. Usually people don't ask what is this theorem, what is that theorem.
Okay, thank you.
Okay, so I'll proceed. Before I proceed next, I mean this is the same thing, but presented in a more generic way. The previous image was for Android, and this is a more typical the architecture of any OS. So I think I'll just skip it because it's the same thing covered. You can have a platform, then you have kernel drivers and so on. So finally, moving on to the architecture of CP or the communication processor. I will just try to put it in a 3D view. Again, you have, since a CP is a processor, so you need to have a driver layer, which I've mentioned as the hardware abstraction layer, which will again abstract the above functionality from the underlying hardware, because you may be using chips from different companies. So depending upon what chip you're doing, again, the above software has to be modified. So to make the software platform independent, this hardware, the hardware independent, the hardware abstraction layer comes into picture. And then on top of it, you have an RTOS or an embedded OS. Because as I said, that the functionality of communication processor is not as vast as your application processor. So you don't have a full-fledged OS, but you have an embedded OS, or basically that is called an RTOS. And then on top of it, you have a platform abstraction layer, which will abstract the implementation of your basic CP or protocol functionality from the OS, so that your again protocol stacks can be independent of which RTOS you're using. So you have just 2 layers of abstraction. Then coming on to the stack, I just tried to put up some of the common modules. There might be many more depending upon which modem you are using, but few of the common modules will be basically first one. If you are talking about AP on the left hand side and your RF, sorry, this is a typo, this should be RF over here. So anything that comes from AP there will be 2 interfaces. One is a radio interface layer and one is data interface. So radio interface layer talks to the application processor and takes all the commands that it is going to give. An example of a command could be when you want to power on your phone, you want to dial a call, you want to receive a call, you want to send an SMS, or you want to turn on the airplane mode, you want to search for a network. All those things are your control plane part. So, but once your internet is connected or your call is connected, everything that goes is a packet. So for exchanging a packet, you have a different interface that is called a data interface. Usually the data rate supported by the data interface will be much higher, because when you are doing browsing or you are watching a video or something, the amount of data that is flowing is huge. Whereas when you just simply want to set up a data call or you want to dial a phone call, the amount of data that needs to come from AP to CP is very small. So that is why you have 2 interfaces. And then the thing is, again, there's a level of left to right abstraction. That means whatever you see at the bottom of this is a modem interface. So different companies manufacturing modems will have a different design over here. And again, if these designs were exposing different APIs or functionalities to the OS, then your OS has to be different for every modem, which people wanted to avoid. So that is why modems usually have a common services layer. So these common services layer will expose APIs, a common APIs with for call, for SMS, for data, for network management, for miscellaneous services, and so on, so that the implementation of the modem is hidden from OS, and then OS can call the common functions, and then this layer will take care of translating the request from AP to the corresponding format which is expected by the modem. And then if the phone is being manufactured by an OEM, for example, Samsung, for example, sometimes they will buy the modem from Qualcomm, they will put their own Exynos processor and make a phone out of it. So in that case, this part comes from Qualcomm, and what we saw from the previous slide was from Android. So now, sorry, from the processor was from Samsung, and then they put an Android OS on top of it. So in order to make things compatible, we define a common radio interface layer so that both the application processor and communication processor can understand the same language, to be very in layman terms. That is why you have this common services layer, and then these layers are implementation of your call functionality. PS is basically packet services or data services. You can see a SIM module sitting here that will basically be talking to your SIM card. You have a data manager which takes care of connecting and disconnecting your data calls. Whenever you move from one location to another, and you're connecting to a different tower or say core network, we'll talk about it later. How does your IP address remain, so that if otherwise if you're moving from one cell to another cell, if your IP address changes, all your data sessions will break. So data manager is basically taking care of all the data handovers. Then MMSS is basically your multi-mode system selection. So when you are operating in a particular area, whether I should camp on 4G network, 5G network, or even if you're, I'm powering on in an area where 4G is available, but in the same area you may have 4G service of Airtel, Vodafone, Reliance, and so on. So, but given my SIM is from, say, for example, Airtel, the device should be able to only search and camp on an Airtel network. It should not unnecessarily waste time in searching for Geo network and trying registration on it. So this multi-mode selection module will take care of basically talking about which network to select, when to fall back. For example, you're moving in a train. So when you leave Aligarh probably and you reach an area where there's no 4G coverage, only 2G or 3G is there, then how does the phone fall back from 4G to 2G or 3G and still continue to give you services? So again, that is called taken care by the multi-mode system selection module. So that is why it is multi-mode system selection. And then you have something called as protocol stack. So you, depending upon how many technologies your phone is supporting, whether it's supporting only 2G or 3G or 4G. So each technology has its own protocol stack, which we'll talk in the later slides. And then after that, there is something called as a common physical layer and common RF layer, because even if your phone is supporting multiple technologies, your RF chip might be same, or you may be reusing the same antenna for different technologies as long as they are using the same frequency. So there's no point of replicating your RF interface or RFIC separately for each stack, because at any point of time, only one or two technologies will be using the antenna. So that is why there is a common interface. And then finally, your data goes to RFIC, where it will be modulated, and then all those things that we have discussed in the earlier slides will take place, and finally it will be transmitted on an analog carrier. So this is a block diagram again for the software architecture of a communication processor. Again, I'll pause here for a moment if you have questions. And I'm open, like any of the experts, because we do see a couple of seniors have joined. So at any point of time, like we have Anand, Abid, or other folks, if you want to pitch in and add some more content, you are most welcome to do it. Open for questions. Because I know this is something very new to you guys. You might not have got through some of the terms. Even if you have a very silly question, please do come up and ask, because it's always good to ask a silly question rather than holding it and not understanding any of the remaining slides. Any questions?
Yeah, this is Sharad here, right?
Yeah, go ahead.
Hello. Yeah, this is all design part. I understand. I mean, it's electronics and computers. I'm actually electrical guy, so I actually correlate with the application part more. So I don't know whether this is part of this forum or not, but I just wanted to the Fourier transform, which is used in mobile application for communications. Is that part of this particular thing? I was interested to understand a little more on that.
Yes, so I think you missed this slide. So all those Fourier transform and processing happens at the RF end. So after modem, we showed that there's an RFIC, right? So all those Fourier transforms and those things, the power amplifiers and transformation modulation is happening, is being done by the RFIC. So it does happen beyond modem. Till this point, we are only talking about the digital data, which is zeros and ones. So once it goes to RFIC, all those things will come over there. And that's why this processor is called baseband processor. That means all your data, whether it is a transmitted data or received data, the passband level filtering, passband processing is done, and finally only the baseband data comes here.
Right. Good. Okay.
So again, for this, to be good at this, you need to be having very good concepts of communication, not just the signals and systems, as my friend mentioned, the Fourier transforms and all those things. You should be very good at your modulation. You should be very good at your communication, because the technology or rather the protocols that will be used in 4G, 5G, and so on, they will be different from your TCP/IP stack. But if you understand TCP/IP stack, you will understand what is the concept of having multiple layers. How do all these stacks combine together and work? So that is very fundamental and very important to understand, to appreciate, and then design these stacks. And then apart from that, you should be having very good algorithms and data structures concept, because just think of one thing. If you have one simple DNS query, let me talk about a very simple packet. DNS query, if it comes from AP and then you are translating it through all these layers that you see in green, and if you try to copy that packet every time, how much time you are going to waste? So it's not just about hardware design, but it's all about software design. You have to design your system so that you minimize the copy, you minimize the number of headers that you're adding from one layer to another, the amount of data that is flowing. So all these has to be a very good software design. If your software design bad, your speed and your throughput performances are going to degrade. Your processors are going to heat up. So all those things have to be taken care. It's not just about writing a C code or something. So usually the languages that are used here, all the things you see in green are usually written in C or C++. Because this is something that is talking to a simple processor. There's a very thin platform layer, a very thin embedded OS. So more of the things are written in C. Sometimes, usually the 5G protocols are coming in C++, because they are using like the STL concept. But all other modules are, you go for any chipset, you go for Qualcomm, Samsung, MediaTek, most of the things are written in C. So you need to have very good programming language, very good communication concepts, not just analog and digital communication, but also your computer and communication concepts. You should be having a good OS concepts if you are going to work in the platform abstraction layer or RTOS. You should be able to connect how your software runs a device. That is what, if you do in RoboClub, right? You are connecting or interfacing different devices to your microprocessor. So it should be having a very clear picture of what we are writing, how to call, how to interface with different modules. That is what is required at these layers. But if you're talking about this, it's more of communication protocols, your software coding skills, your operating system concepts, and these things, and your algorithms, definitely. Because for instance, as I told you, that MMSS module is taking care of scanning all these technologies, right? So if you don't have a very good searching algorithm in place, you're going to spend a lot of time in searching your network. And one typical example is when you travel from one city to another. For example, you travel from Aligarh to Delhi or Delhi to Bombay. The first time you power on your phone after getting down from the flight, it takes a lot of time. It takes typically 1 or 2 minutes to search, right? Unless until you're on a geo network, which is only LTE. So that is because it has to scan a lot of frequencies. So unless until you really have a very good searching algorithm, your phone's performance is going to degrade. And that is when the customers come and say, hey, this phone doesn't give speed, or this takes a lot of time, it hangs a lot. So if you don't have a very good OS design, your phone, all these because everything will run as a separate task or a separate process from a OS perspective, because it's running on an operating system. So if you don't have very good memory management and very good process management, everything is going to clog your processor, and then your phone will become slow. So again, you need to be having very good OS concepts. That is not required in AP to a greater extent, because there's a like kernel and then libraries and frameworks. So most of the time you are using APIs. But since we don't have a very strong OS here, it's a simple OS. So you should here also you need to take care of how your process management is working, how you're calling messages and so on. Right? Any other questions? So with that we come to the end of the first section. That was basically the software architecture of phone. Then we are moving on to the network side, or basically the communication part of the different technologies. So one fundamental concept that I would like to touch that is mainly for second year students. Because, I mean, if you are aware of it, please let me know and I'll skip it. So there's something called a circuit switching and packet switching. So these terms I'll be using very frequently, and that is why I've taken them on this slide. So there are two types of communication networks. One is a circuit switch network and one is a packet switch network. So in circuit switch network, whenever you are establishing connection between two devices, be it two phones, be it two laptops, be it two landline phones, anything, your connection from one device to another is frozen, and that connection is dedicated to you unless your transaction or your call is completed. So that means all your packets or all your data that you are sending will follow the same path. And at the same time, that path is dedicated to you. So nobody else can use it. Even if you establish a call and keep it on mute, you are wasting resources. But you don't have any data to transmit. But the network is not going to assign that resource to anyone else. So that is a drawback of circuit switching. So that means if a dedicated circuit or a dedicated path is allocated to you, you are wasting resources. But the advantage is that there's a dedicated flow, so nothing is going to be lost. Everything is going to be in sequence and so on. But at the same time, when you talk about packet switching, all the network ensures is whatever you send will reach the end. Whether it reaches the same path, whether it takes different paths, it doesn't matter. So for example, in this figure on, you're establishing a net connection from terminal 1 to terminal 6. So this is the path that is frozen. So anything that you send will always take this path that is shown in blue over here. Whereas in case of packet switching, every time you send a packet, be it a data packet, be it an audio packet, anything, it will take different paths. So from here to here, there's only one link, so it has to take it. But this switch or this node will decide whichever is the least loaded load, and then it will transmit it. So this is the receiver on the right hand side, and this is the transmitter. So what this node has done, it has transmitted two packets here on this path, and then it has transmitted this packet, another two packets on this path. So finally, they travel different paths, and they are reaching the endpoint. So when you have packet switch network, so for example, this path is there, right? So had there been one more system, this path can be shared across multiple systems. It's not necessary that this path will be frozen only for terminal 1 and no one else can use it. So the key advantage with switching is you can share your connections, and then efficiency increases. For example, on one path, if 10 people are able to communicate using one path, that means you have a much higher efficient system as compared to when one path can be used by only one user. So this is a key thing that has been probably exploited when in the development of communication networks. All right. So then moving on.
What are the practical life examples of the two things?
Circuit switching is used in all your landline networks, right? Whenever you have a landline phone, it always uses a circuit switch. In mobile communications, 2G and 3G used circuit switching for voice calls.
Okay.
Whereas every data connection, whether it's a Wi-Fi connection, not a Wi-Fi LAN connection, mobile data starting from 2G, 3G, 4G, so on, everything is using packet switching. And a key point to note, from 4G onwards, when you have a VoLTE call, that is using packet switching even for voice calling. Circuit switching has closed because of its inefficient.
So can we say all data communication happens on packet switching, and voice communication is still on circuit switching.
Data path is, you are very much correct about data path, but voice communication, it depends upon what technology you're using. So if you are using anything prior to 3G, it was circuit switched. 4G onwards, it is even audio communication is on packet switching.
It's still an experience. I'm putting it in very plain terms. Like I'm on a video call with you. If I make a call over WhatsApp, voice call over WhatsApp, this call with you will continue. If I go to my voice call of the phone, actually this meeting will end for me, and I'll have to rejoin. I don't know. I mean,
Yes.
I'm on
Yes.
4G. Yeah.
Yes.
Yeah.
So
Okay.
that is because your phone or your network might not be supporting VoLTE. I'll come to that. So in case you're on a 4G network, your phone supports VoLTE, then even since your voice call also uses packet switching, then your packet data communication or a video call will not end. But if your network is not supporting VoLTE, then you have to fall back to circuit switching on 2G or 3G to make the call, and that is the reason why your data connection will terminate.
Okay, I understood your point, but I mean, I'm not an expert on that, but I'm on Airtel, so things are automatically configured these days. So till now, this has been happening to me since I have started using a mobile phone. So anyway, we can proceed, but
Yes, Airtel supports VoLTE only in selected circles. So I'm not very sure Airtel supporting VoLTE in Aligarh or not. If it is
yeah,
not supporting, then definitely it will be a fallback to 2G and 3G.
yeah, correct. So as a user's experience, I
Yes,
understand voice call stops everything else. Okay.
correct.
Okay, okay. Yeah, thank you.
Okay, so now I will quickly touch upon the evolution of mobile technologies. So 1G was probably that was the technology that was called AMPS or Advanced Mobile Phone Systems. That was an analog communication system where there was no digital thing involved. That was started, I mean, deployed from 1981. Most of you might not have been born at that time, so you might not have seen that. 2G also, it came around 91. 2G only supported voice and SMS. GSM technology, Global System for Mobile Communication, that was launched in 1991. It only supported voice and SMS. It did not support data. Most of you guys, when you fall back to 2G today, you get data connectivity, though very poor speed, because that is because of a different reason. But 2G, when it was launched initially, it was not supporting data. Then a little later, there was an addition done to it to the 2G network that was called GPRS and Edge. GPRS stands for a Global Packet Radio Service, and this thing is evolution for data something. So these were in addition to that existing 2G network, so that you can support data services also. How it was done, I'll cover in the coming slides. But the difference was, the similarity was both GSM and GPRS were using the same radio technology. So that means whatever modulation schemes, whatever radio things, whatever frequencies were used, so that was same. That is why it was not given the basically the name of 3G. So using the same infrastructure with some changes in the network side and some changes on the device side, but using the same radio technology, using the same communication systems, data connectivity was added. So it was called 2.5G, and that is what is commonly known as 2G today. So if you talk about the 2G of today, that is actually 2.5G. And then so this was using a voice circuit switching for voice and packet switching for data. Then came 3G, where the channel bandwidth was increased, and so when 2G was launched initially, what you got speeds was like up to 144 kbps, combining GPRS Edge. But then when 3G was announced, it brought up the internet speeds up to around 2 Mbps initially, and then with a lot of evolutions, because you see that 3G came into picture around 98, where the key technology was called UMTS, Universal Mobile Telecommunication System, or wideband CDMA. So this increased the channel bandwidth. People who have studied a Fourier transform or communication systems, you would be knowing that there's something called as a bandwidth of the channel, right, or bandwidth of the signal. So the higher bandwidth you give, or rather the wider the frequency you give to the mobile, the more data that you can send. So that was one of the key reasons why 3G was able to provide you higher speed. And the second reason was the modulation technique that was used in 2G and the modulation technique that was used in 3G. So basically modulation is when you convert your digital data into analog data, right, on the analog carrier. So the technique that was used to map it was changed in 3G, and that also gave a better data rate. So this you will study in your analog communication and digital communication courses in third year and fourth year. You can keep a note of that. But so for example, you have BPSK, QAM, and so on, QPSK. So all those things were changed. And then in around 2008, 4G was launched. 4G is basically the technology is 4G or LTE, long-term evolution. Sorry, in between that, there's some enhancements done to this thing to 3G, where the data rates which went up initially from 2 Mbps all the way to probably 20 Mbps or so. Though you are not able to get that practically in the field, but technology does provide you speeds of up to 20 Mbps or 30 Mbps over different configurations of uh, advanced 3G, which is called HSPA, that high speed packet access, or HSDPA, which is high speed downlink packet access. So initially downlink was optimized. So downlink is called anything that is coming from the network to your phone, and anything that you send from the phone to the network is called uplink. So initially only the downlink was optimized, because if you practically look at the usage of your phone, most of the time you are downloading something from the internet, whether you are browsing, whether you are watching a YouTube video, you are watching and doing Facebook, or you are downloading a big file. Most of the time you are downloading it. You are not sending a lot of data to in the uplink, and that is why the focus has always been on optimizing downlink first, and then comes uplink. So I mean, HSDPA came, and then HSPA came, and HSPA plus came. So all these things now increase your data rate. So now, I mean, when we moved from 2G to 2.5G, I said your radio communication parameters were kept same and network architecture was changed. Here, the network architecture was kept same. Your radio parameters were optimized. Your channel bandwidth, your modulation techniques, your CRCs, and all those things that are done in the signal that were optimized so that you can get a higher speed by reducing your losses that happen over the radio interface or the air link between your phone and tower. So just to add one thing, most of us know that mobile is a wireless technique, but in this system, the only wireless link is between your phone and the tower. Anything beyond the tower is a cabled network. So all the bottlenecks, all the problems of low speed, high speed, call drops, everything is only because of the link, the wireless link between your phone and the tower. So all these technologies that have been evolving, they have always focused on improving or making this link more robust so that your performance increases. And then 4G came in 2008, where the focus was providing a higher speeds. And then 5G came probably last year. The deployments have started from last year. And this technology is called NR, or new radio, because while the changes from 2G to 4G happened, they were building upon the incrementally. But from 4G to 5G, they radically changed the air interface. I mean, there are two different frequencies that are used for this. We'll talk about it later. One is the millimeter wave, and one is the regular frequency. So this evolution that we talked about is called as a 3GPP evolution, because there are two families of mobile technologies existing in the world. One is called a 3GPP family, which is 2G, 3G, 4G, I mean GSM, UMTS, 4G LTE, and NR. In parallel to it, some countries were having their a different technology called 3GPP2 technology family, which is basically the CDMA family, which started off with CDMA1, which was a 2G technology. Then CDMA1X came, which was 3G, and then 3G, because the speeds of CDMA1X were same as 3G over here. But typically, this technology should fall into the category of 2G, right? But since the speeds were equivalent to 3G, so that is why it is called 3G. And then there were certain evolutions that were called EVDO and then CDMA, I mean EVDV and DVO. So from here to here, again, there were changes made on the radio network and also on the network design so that you can get a higher speed. But the only difference was CDMA 2000 supported both voice and data, whereas this supported only data. So if you are able to convert your voice call into a data call, your call will work, just like it happens when you make a WhatsApp call. So although you are making a WhatsApp audio call, but that is not using your circuit switching, or it is not using the technologies of voice call. Everything that you speak goes as a IP packet. So as long as you're able to convert your audio packets into, audio communication into packet network, it was supporting it. So it evolved up to 3G, but then after this, both the bodies decided that there's no point of continuing to competing technology in the world, so they converged from EVDO to 4G. So after 4G, only 3GPP technologies have evolved, and this family has been shut down. So this family was primarily used in US and Japan sometimes. So gradually they converged, and then finally on the 4G and 5. I mean, 3GPP line is going on. So when 6G comes, that will also come here as a product of 3GPP project. So this is how the technologies evolved.
Yeah, Umair.
Yes.
Yeah, two things. This Industry 4.0 is on 5G, right?
Sorry,
Industry 4.0 is on 5G, right?
I'm not able to make out.
Industry 4.0 protocol is on 5G communication, which we are talking on industrial
Uh,
automation.
yes. So 5G is typically designed not just for mobile communication, but it's for literally for everything. They want to connect every device in the world to a cellular wireless network, and that is why you don't see a phone icon over here. Whether it's car communication, industrial automation, mobile communication, IoT, your smart meters, everything will converge into the same network. Because till 4G, the system capacity was not good, not enough to accommodate all such devices onto a single network. But when 5G was designed, it was designed with the vision to remove all such bottlenecks and then bring all the smart devices, or literally every device in the world, into the same network.
Right, right. Oh, and another thing, one thing comes to mind, like I don't know, there is an international regulatory body or something. I mean, I was just curious
Mhm.
to know where they decide that we have developed enough now to call it a 4G or a 5G or a 6G. I mean,
Yes, that is the last slide of my session.
okay.
Okay, so quickly moving on. I mean, as we talked about, different countries started off with different technologies, and finally they kept moving and converged. So globally, this GSM, GPRS, Edge, WCDMA, HSPA, HSPA Plus, and LT, and LT Advanced, LT Pro, and then 5G. This is the most commonly taken path, but different countries like Japan, US, because usually US wants to do something different from Europe. So they just started off with CDMA, and then they came up with CDMA 1X, EVDO, and finally after EVDO, since there was no further evolution on the 3GPP side, so they converged into LTE. So this is a typical path of United States carriers, but in US there are four major carriers: Verizon, AT&T, T-Mobile, and Sprint. Sprint is now merged with T-Mobile. So Verizon and Sprint took this path, whereas AT&T and T-Mobile followed this path. They started off with GSM itself. But then, yes, Japan and China, I mean, they follow different paths. For example, Japan came to 3GPP line only from 3G. And then I think a couple of countries are not covered here. So China also is following a CTDMA and so on. So this is just for informative purpose, like different countries follow different evolution paths, and then finally everyone has converged to 4G LTE, and then they will be following 5G NR and then 6G and so on. So now, with a brief introduction of 2G, 3G, 4G, we'll now look into how the mobile network looks like. So typically, if you look into a mobile network, there are four fundamental pillars, as we call it, or components. First is obviously your mobile phone or mobile station, that is typically called. Then you have something called as a radio network. Radio network is typically what you see as a tower and a machine associated with it. And then there's something called as a core network. Core network is basically what is going to provide you the functionality of your call and data. And finally, the last entity is your terminating side. So if you are making a voice call, you are basically going to call either a mobile phone or a landline. If you are going to use internet services, you are going to contact one of the web servers, right? For example, if you open Gmail, you're going to talk to a Google server after going all through this. So these are the four basic components. And then all the design changes that have happened. If we talk about the radio level changes, so those changes have happened between the mobile station and GRAN. If we talk about the core network changes, where I was talking about network architecture, so that happens basically in the core network. So now Since I told you that 2G and 3G supported both CS and circuit switched and packet switched domains, so there were two core networks associated with each radio network. Whereas from 4G onwards, there's only since it is supporting only packet switched, there was only a single core network. And then every technology, the name of the radio network has been changed, right? So in 2G, it was called GE-RAN. RAN stands for Radio Access Network. In 3G, it was called UTRAN, or Universal Terrestrial Radio Access Network. And then in LTE, basically, every terminology was, there was an E added, that means evolved. So this is called EUTRA, where it is called Evolved Universal Terrestrial Radio Access Network. So when you say RAN basically talks about the tower as well as the radio network protocols involved over here between the device and the network. Whereas this component itself is called basically eNode B. So in 3G it was called Node B, in 2G it was called base station, and then it is called eNode B or evolved Node B. So I mean, Node B, when the system was designed, it was just given some name that, okay, this is called a Node B. We'll rename it later. But when the standards were frozen, they did not change the name, and it went on as Node B. So in 3G it was called Node B, and then it is called evolved eNode B, and then 5G it is called G Node B. Right. So I mean, here we see that in PS domain, finally it is going to end on an internet network. In mobile domain, it is going to end on a mobile station on the same network, or it's going to be routed via PSTN network to your cellular calls. So now we'll quickly look into details of these clouds that we have observed. So you can see a tower over there that is typically called your base station. This is the 2G and 3G network architecture. So you have a radio connection that is shown in orange, and then there's something machine that is typically called your BSC or base station controller. So this is called a BTS, base transceiver station, and this is called a BSC. So these two blocks form your radio network or RAN that we talked about. Then in the core network, there are a couple of things. Your MSC, which is typically called a mobile switching center. This is the main entity that handles all your calls. Whenever you make a voice call on a circuit switch network, MSC is basically the entity that is going to route your calls, decode all the signaling, because when you want to establish a call, you're going to send some message. There's a defined format of message of a request that the mobile will send. So that will reach MSC. It will decode what type of call it is, where to route it, whether it is to be routed on my same network, to a different network, to a landline, and so on. And then finally, it will forward it to PSTN. So PSTN is a national backbone network for all circuit switched networks. So all the circuit switched telecommunication system in the country is connected to the PSTN network. That is called public switch telephone network. So if you want to call from Airtel to Vodafone, your MSC will route the call to PSTN, and then from PSTN it will come back to the MSC of Vodafone, and then it will be routed to the respective base station and then phone. So that is how it's going to be routed. Similarly, if you are going to make internet connection from here, it goes all the way to your this is a 4G basically SGW and PGW. So there's SGSN and PDSN that comes into a picture for 3G. So these are the two components serving gateway and GGSN, GPRS gateway serving node that is going to route your internet IP traffic to the internet world. So this entity is basically responsible for all IP address translations, IP address allocation. Whenever you power on your phone, the first thing you need to get to set up a data connection is an IP address. So when you send a registration request to the network, it all goes all the way from here. It will come to MME or MSC, SGSN basically. So SGSN will do your registration. It will fetch an IP address from a GGSN, and then it will allocate to you. And then once the UE is able to get the IP address, then only you can do any browsing, you can do any WhatsApp call or something. So typically, this is the architecture of a 2G, 3G network. In case of 4G, the things are a little modified because now there's no CS part. It's only a packet switch network. So we have a EUTRAN where all these towers are called eNode Bs. They talk to the phone, and then these are connected to 2 or 3 main components. So MME is basically your called mobility management entity. So this entity takes care of your registration. This entity takes care of when you're moving from one place to another. Say, for example, you powered on your phone in Aligarh and then you move to Hathras. Hathras will be served by a different base station. So you have to be moved from one network of the same operator to another network. So that is basically taking care of all your mobility management, all your roaming things. This is basically doing of that. Along with that, it is connected to something called as an HSS and AAA server. So the first thing that you when you power on your phone is the network should authenticate you, right? If you're an Airtel subscriber, you cannot go and camp on a Geo network. So that is the authentication that happens with the network. So these are the entities, a home subscriber substation and AAA server. They are the entities that are responsible for doing your authentication. So that authentication happens, these servers will send one secret code to you, to the phone. That code will be sent to the SIM card, and only the SIM card node has the keys to decrypt it and generate a response. Then SIM card will give you a response. That response will go back from the device all the way to MME, and MME will validate that the response that the device sent and the expected response that was given to you by HSS and AAA, are they matching or not? If they are two are matching, that means you are a valid subscriber. If the response doesn't match, that means you are a fake, not a valid subscriber for that network, and then your registration will be rejected. So that is how your authentication happens, and that is where the key role of SIM card comes into picture. Because if they want to implement this authentication mechanism in the phone, operator has to reveal those mechanisms and those keys to every phone manufacturer in the world, and then that those things can go public into the market, and then there will be a lot of hacking happening. So that is why, since the SIM card is manufactured by the operator itself, he will embed that algorithm, those keys, all those passwords, in a very layman term, into the SIM card, so that only the SIM card knows. All the phone has to do is receive some code from the network, give it to the SIM card. SIM card will make a response that is not understood again by the phone. Phone will simply give that response back to the network and let network take care whether this is the correct response or not. So that is how authentication happens. And then all your data plane thing, like when you do your calling, or you want to browse internet, all the packets come from the tower to the serving gateway. From serving gateway, it goes to the PDN gateway, and then PDN gateway, it can be connected to your IP network. So that is how your data session, your VoLTE call, your voice calls, all those things work. So now one fundamental difference in 4G from 3G was, in 3G you can be connected only to one internet network, but 4G provided you the concepts of PDNs or APNs. So here you can be connected to multiple networks at the same time. So a typical example is when you, for example, when you use a Geo phone, when you browse your data, all your packets go to internet and then to Gmail or YouTube or Facebook or whatever you do. But when you make a call, the call doesn't go through internet. It goes through the IMS network, which is called an Internet Multimedia Subsystem. So because this is a specialized network providing you higher quality of service for voices, because the only drawback for PS or packet switch networks was the quality of service cannot be guaranteed. But if you want to make a call and you cannot guarantee the quality of service, and your packets are getting here and there, it's possible, let's say you spoke 3 words, how are you, and all the three words are transmitted by the device as 3 different packets. And in case of PS network, since the packet in order delivery, that means the first packet may be the last one to reach the device, reordering may be needed. So ultimately the receiving device will reach how are you, you will receive where you are, how. So that is the reason why you need to come up with a separate multimedia network, which will give you guaranteed quality of services. I mean, there are a lot of changes happening, but I'm talking only in terms of layman. At the same time, if there are certain services that operator wants to provide only for its own subscriber, for example, Geo is providing you all this Geo TV and My Geo and Geo Savan, etc., which may not be available over the internet. So Geo may put their own private network over here, and all such packets will be routed to that internet. So those sub-services can be given only to GS subscribers instead of putting it on the internet. So that is how 4G has evolved. I mean, providing multiple packet network connectivities. Again, 5G, I'll not spend a lot of time on this. I'll take the question just after this slide. So this is the 5G network architecture. The functionality of AMF is same as MME. SMF is same as your serving gateway. UPF, you can say it is same as PDN gateway. PCF and AF is basically your HSS, sorry, UDM and EUSF is basically your HSS and authentication related stuff. And DN, what you see is your IP network that we talked about. So DN is data network, UPF is basically your PDN gateway, SMF and AMF are taking care of serving gateway and MME. Your eNode B, eNode Bs are now called GNode Bs. There have been changes in the radio network. That is why it is called as NR or new radio. And these are the standard names of the interfaces. So every component is connected by some interface, and every interface in every technology has a name. So all these are numbers N1, N2, N3, and so on. When you study standards, they will be giving detailed description of how these are going to talk. One fundamental difference of 5G from 4G from a user perspective is till now only you could connect to a 4G network only via mobile towers, right? If you connect to a Wi-Fi network, you are not able to get Wi-Fi services other than calling, that is called EPDG. But 5G also gave you that even via Wi-Fi or non-3GPP technologies, you can still connect to a 5G network. So if you're connected to a Wi-Fi or if you're connected to a CDMA network, CDMA network can still connect to AMF and then provide you 5G services. So some of the services which are guaranteed by 5G radio network will not be available to you because you're connected through a Wi-Fi, but still some of the services which are provided to you by core network, for example, network slicing and MEC and so on, they can still be availed by these devices. Somebody had a question?
Yeah, I was just adding that when you were explaining difference between call over internet or the dedicated network, yes, reliability over the dedicated network is good, but over internet we get the quality of call is quite improved. So that's what just I was thinking.
Yes, because there have been a couple of evolutions at the same time. For making a VoLTE call, basically, if you make a WhatsApp call over a PS network, at the same time you make a VoLTE call over a voice over LTE call from your phone, the quality will be different because VoLTE call is treated as a regular packet data, whereas a VoLTE call is treated as a voice call over LTE or voice call over 4G. And the quality of services that are granted to a voice call over LTE are hugely different because of certain improvements that are done. So yes, it has been improving over the time, and it's going to improve. But yes, it may or may not match the quality provided by circuit switch networks.
Right. Thank you.
So the last thing on this topic is basically when I said that there has been a huge change in the 5G design, network design from 4G. So it required all the manufacturers, all the vendors to build up the completely new protocol for the radio network as well as the core network. So in order to make sure that the deployment of 5G keeps on going, even though some of the components may not be ready, we came up something called as a dual connectivity. I'll briefly touch upon it. But as I told you in the initial session, in initial part, that the main bottleneck is your wireless link between the phone and the tower. So if we are able to somehow improve this, you'll be able to get a higher speed. Obviously, you may not be able to get some of the other services which are provided by 5G, but at least your speed bottleneck will improve. So that is why what standards allowed you and what operators have been doing around the world is most of the network side vendors are ready with with their GNode Bs, but the core network is not stabilized because the standards were not frozen earlier, and then the development started late. So they wanted to fix this radio network first so that you're getting a higher speed, and then you gradually, once the core network is ready, you will get better services, other than the higher speed. So there are different architecture options that have been proposed in the standards, how you can connect or use 4G and 5G together unless and until 5G network is completely ready, so that you still get a higher speed, but at you're still using the 4G network. So option one is basically when you are on a core LTE network. So you are connected to, your phone was connected to LTE eNode B, and then you are using LTE core. So LTE core is called EPC, Evolved Packet Core. This is the name of LTE core network. This is the name of LTE radio network. And this is the final goal that everyone is trying to reach. it will use a 5G G node B, and it will connect to a 5G core network. But since this is new, both of them cannot be stable. We have come up with multiple intermediate options. So as long as both of them are not stable, we'll use some way or the other to connect. So right now, the 5G deployments that are happening are using option 3, different flavors. So 3, 3A, 3X. What they try to do is, in this, we believe that the core network is not ready. So we are still using the 4G core network, but the radio network, we are using LTE as well as 5G. So these are different configurations. Red one is a control plane. What you call? The red is your data plane, and the other one is basically your control plane. So what they're trying to do is they are trying to connect all the signaling messages when you want to connect, when you want to disconnect, or when you have any important message to be sent to your to the network, which is small in size, but it is very important. So for that, you are using LTE radio network and LTE core network, because this is already a stable network for almost 11 years now. But for your data packets, the core network, or SGSN, as we saw here, is going to send the packet, instead of to LTE radio network, it is going to send to the 5G core radio network. Now, since the 5G radio network and 5G UE radio link is improved, it can provide you higher speed. That is why how you get a higher speed when your packet data is coming from 4G core to 5G radio network and UE. So this is called a dual connectivity, where you are connected to the network both via LTE and 5G. So these are all the intermediate options. Option 3 is there, option 7, option 5. I'm not going to touch all of them in detail, but these are the various intermediate options where you will start with option 1 and then finally end up in option 2, which is the 5G standalone network. Finally, so sorry, I think so. This is about the network architecture. If somebody has any questions, probably we can take that up, and then finally we'll be discussing the TCP/IP, the protocol stack, and then wind up the session with some more topics at the end. So I am working on the handset side in my company. Abid is an expert in these things because his company is mainly working on the network side. So if you have any questions on network side, probably Abid will be able to answer better. If you have any questions on the handset side, I'll be able to answer. But the network architecture remains the same, and irrespective of whether you're working on the handset side or the network side, you should be aware of this. You should be aware of how the key interactions between the components are happening. So questions?
Actually, can you hear me?
Yes, very much.
I have a question that so there are multiple access schemes. So you have told CDM, and there are different versions of it. You have a slide about it.
Yeah.
So are they still in use, or like they just use the advanced version of those? And
So
there's
now,
I have studied some frequency distribution schemes too. So are they still in use? Because I've studied about the
no,
basic
actually,
version too.
there are two different things. One is CDMA is code division multiple access, and the other CDMA is a technology. So the code division multiple access was used still used in 3G, and even OFDM uses a flavor of it, right? But the CDMA as a technology is no more used because since CDMA was stopped after 3G, so no other operator in the world is using CDMA for 4G. It is on migrated to LTE. But if you talk about TDMA, FDMA, and CDMA as multiple access methods, some versions of are used. LTE is using basically an OFDM, which is a modified version of those concepts.
Okay, so and one more thing, that all of this 2G, 3G, and 4G stuff is about the mobile that is produced by Samsung or Vivo or any other manufacturing company. So like if the Airtel and network companies come into the picture, they are just using our identity. Like they have been given a bandwidth and they are just charging us for using that bandwidth.
No. See, if you look into this slide, you have a phone, uh, you have this network. So all this network is owned by Airtel or any other operator, though the components will be manufactured by different companies. They will buy the components tower from somewhere else, HSS, HLR from different vendors. But it is they who are going to install and maintain it. So, and when these components are designed, they have to understand the same protocol or the same language the device is using, right? So all these technologies that we are talking about, they are defining some language or some protocol that is being used by the device and the network components to talk to each other. So these define the methods or the languages, and then the operators are installing these networks, providing your service and charging you. Yes.
So can't we have a just single network like BSNL is a governmental organization, so all the bandwidth is given to this organization? Can't we do that? Like,
I mean, how many operators we are going to have? See, telecommunication is a business, right? So as many people want as they can enter into it. But the amount of frequency that every country and every state, I mean, every country has is limited. So that government decides that how many operators are going to allow in a particular area, depending upon the available frequency. But yes, there's no restriction why there should not be multiple operators. If there are multiple operators, probably there'll be a lot of monopoly, right?
okay, so like, and one more thing, like base station and the mobile that is that you are holding, that they're both configured to 2G, 3G, and 4G. So like, matlab, if I have a 2G phone, then I can still use the 4G base station.
No. If you have a 2G phone, you cannot use 4G. But if you have a 2G, 3G phone, and the phone will first try to use 4G network. If it is not able to find 4G services, it will use 3G. If it is not able to find 3G, it is going to use 2G.
Okay, thank you.
So that is what I discussed, the multi-mode system selection module, right, in the communication processor. So that processor takes care of deciding whether I should be using a 2G, 3G, or 4G network at any point of time.
Okay, thank you.
Any other question?
Yeah, hello, sir. Am I audible?
Yes.
Yeah, sir. I have a question. Like, being a second year student, so suppose if I want to do web development or programming language, I have something available online that I can practice on. So, but when it comes to networking or designing concepts, so how should one do that hands-on? Like, we can't memorize every concept. If we are doing it now, so how should one get on hands-on practice in these?
The first thing is probably you need to understand these protocols. First, you should start off with computer networks, the TCP/IP protocol. Then you should try to implement this socket programming in your language. I mean, C language or any other language, Java, whatever you're doing. So once you are able to set up or you are able to make a communication application over the computer networks, then probably you can try to understand uh, these concepts. And again, if you want to implement, I mean, we have not yet talked about the protocols, but all these technologies will be having some rules, some standards, some protocols, and everything is going to be implemented in a language. So if you are going, you need to understand that and write it, write a code for it.
Okay, sir.
So it's more of coding. But if you
Yeah.
are only interested in application development or app development, then obviously, I mean, you don't need to do all this.
Okay. Thank you.
And then for simulating, like if you, so for example, if you have written a code and you want to simulate these protocols, there are multiple simulators available on the internet, like NS3 or those things. So you can learn them and then simulate any of the protocols. You need not have a lab for it.
Yeah. Thank you.
So NS3 is basically one tool which you can learn for simulating all the protocols. So the next thing is basically the protocol stack. So till now we have seen what are the components, but now we'll see how these components are going to talk to each other. So just like in a computer communication network, you have basically a TCP/IP stack. This is a simplified version, and this is a 7-layer model. So you have an application layer, you have a transport layer, you have a network layer, and then you have basically data link layer and physical layer. So till network layer, it is common for all packet switched or IP networks. But the data link layer and physical layer depends upon what technology you are using. If you are using data connection over Ethernet or LAN, your data link and physical layer will be based upon LAN technology. If you're using over Wi-Fi, these two will be related to Wi-Fi. If you are using mobile data, these two things will be according to the mobile network standards. So this is now what we are going to talk about. And these are the things that are actually implemented when we talk from mobile station to the radio tower or the base station, and then to the core network. Anything beyond data link layer is actually transmitted transparently by the core network to your web server. So I'll just check that. So this is an example of a core network protocol. So you have your phone here. This is the G node B or the tower, 5G tower. This is UPF, basically your 5G core network. I mean, just you can treat these two together for now. And this is your data network or the internet world or the basically your web server. So what you can see that data link layer starts from 5 all the way till SDAP. So this is basically what we call as a data link layer and file layer. Anything above it basically is your IP network, right? What we have seen here. So network layer is here, the PDU layer you can say, and then data link layer starts from SDAP all the way till MAC, and then you can see a physical layer or a file layer. So these are the different protocols that are used in mobile communication network. Physical layer is basically your radio layer that takes care of all the modulation, which frequency to use, how to reduce the errors, and so on. MAC layer is a medial access control, which basically when multiple users are trying to access the same frequency, same channel, how to avoid collisions. If, for example, you have a same frequency and 10 of you start making a call, then all the transmissions will collide and the base station will not going to understand anything. So this is going to control that how multiple users can be spread out. And then a lot of functionality over the MAC layer. Radio link control is basically taking care of your flow control. So if you are sending a lot of packets and the packets are getting lost, then it doesn't make sense to keep transmitting it. For example, you have 10 packets to transmit, and if you transmit packet number 1 and 2, that is not reaching the network because of some failure. It doesn't make sense to send all the 10 packets. You have to retransmit 1 and 2 first, make sure that they are reaching, and then only proceed. So this RLC layer takes care of the flow control, something similar to a TCP, but the thing is TCP takes care of the flow control between your UE and the web server. But if the problem is between UE and the tower, I mean, if you keep waiting for the TCP to retransmit, you will waste a lot of time. So RLC layer takes care of retransmissions between the device and the radio network. PDCP layer is taking care of ciphering, basically, and integrity protection. So I'm using two terms, ciphering and integrity. This means that since wireless link is an open link, anyone can attack it. So all the data that you are transmitting from the device to the wireless network has to be encrypted. If you don't encrypt it and somehow people are able to steal your keys, then anyone can download your confidential data. Right. So that is why PDCP has to take care of your ciphering, integrity protection, and integrity protection is basically, let's say your data is encrypted, but somebody else says that, hey, this packet is from Umair, please transmit it to so and so server. So how does the network know that this packet actually came from Umair? So that is called integrity protection. That means to verify whether whether the sender is actually who he claims to it or not. So that is integrity, and then SDAP layer is basically providing quality of service thing. So these are the different layers that are involved in a communication network. So whenever you get an IP packet, all these layers will do their functionality. They will make sure that the packet reaches the tower, and then the tower is going to use another set of protocols, transmit it to the UPF, and then UPF is going to use basically another set of protocols to send it to data network. So when the packet reaches your web server, all it will do, it will remove these headers, and then finally the IP packet will be given to the network layer on the server, and then it will be as good as your device is talking to a server in a typical TCP IP fashion. So this is the protocol stack when we are talking about user plane data or the actual data packets that you're sending. But before setting up the connection, as I told, there are a lot of processes that happen. So those processes will happen only between device, G node B, and UPF. So to register your phone with the mobile network, you don't need to talk to a web server, right? So this component goes away straight away. So this is basically the functional your stack for registration procedures, where is basically you have a device, MAC, RLC, PDCP remain the same, but our PDCP, instead of having this the network layer, transport layer, some other mobile protocols come into picture, that is called RRC, radio resource control, mobility management, and session management. So these three layers will make sure that you are able to register to the network, your authentication is done, you are able to receive the services on the network, and at the same time why you need to register with the network, because if your phone is in power off mode and you move from one place to another place, then the network doesn't know that you have moved from here. So if you have an incoming call, network will not know whether you have whether it has to send this call to tower number 1 or tower number 2. So it is that is how once you perform your registration, then the network knows your location, that okay, this particular mobile is registered under this tower and this core network. I have to send any incoming call or empty data, that is called mobile terminated data, to this tower and to this core network. So these basically three layers talk about registering your phone, making sure that you're authenticated, making sure that when you move from your home location to your roaming location, all those things are taken care by mobility management. Resource control takes care of adding radio channels and releasing the thing. So one key concept that happens in mobile communication is, suppose you power on your phone, right? You sent one WhatsApp message and then you kept the phone in your pocket. So once you have kept the phone in your pocket, you're not transmitting any data. So there's no point of keeping the radio link between you and the tower active. That because that's a shared link and radio resources are really scarce. So that can be released and given to someone else who wants it. So what happens? Your IP connection with the network, core network remains, but this link is released so that this link can be given to someone else. Now, when you want the data to send data or receive data, something, this link will be brought up again. So RRC layer basically takes care of releasing this connection and then establishing it again. Whereas NAS layer takes care of talking to the core network, maintaining your registration. So this is basically the control plane thing. If you have any questions, I know this was a little difficult for the second years guy especially, but if you have questions, I'll be happy to answer them. So these are the protocols that we need to study. I mean, usually people working on CP protocol stack, they understand these protocols. There are, I mean, standards for it. There are rules for every layer, how to do, what to do, when to do. Those things, we write that in a code and implement it. Just like you might be writing a code to implement, say, for example, binary search. So binary search, you know that these are the steps that should happen in a binary search, and then you write a code for it. Similarly, the standards will tell us, okay, for PDCP layer, these are the steps that you have to do. If the packet has failed, what to do? Packet has come, what to do? If you have to send a packet, what to do, and so on. So all these are a set of rules that we develop in language. So if you want to enter this domain, you should, I mean, nobody will going to expect protocol knowledge from you, but you should be able to have good knowledge of these protocols and be able to implement or write a code for anything. Your coding skills are very important over here. Questions? I think I have just 3-4 more slides. That's all.
So, Umair bhai, I think you have minimum time left now because it's 7:50. So I think you can, go over your other slides.
Yeah, I think I have, 3 or 4 slides. Let me quickly try to go through if people want, unless people want to break. So somebody was asking about the standard bodies. So these are the standards bodies that are basically working on the different mobile standards. So ITU is a great, it's the biggest body, you can say, International Telecommunication Union, that is formed as a treaty by UNO. So this is defining what a particular generation should do. It doesn't define any technology, 3G, 4G. It says for any technology to be called a 5G technology, it should meet these requirements. It should have a minimum speed of, say, this much. It should have a minimum latency of this much. Latency is basically the time that is required for you to send a packet to the network and get a reply. Right. So if you're, for example, if you are sending a WhatsApp packet, it hardly matters how much time it takes to send, because all these times are in milliseconds, right? But if you are doing some gaming, if you don't get your packets within a fraction of a millisecond, you cannot play a game. So latency is very important. So this basically body defines that for any generation, what should be the performance standards. And then all these bodies you can see over here, GSMA, IEEE, 3GPP, all these bodies are going to take those requirements, develop their technologies, and present to ITU for recommendation. So, and then ITU will approve those if the standards are meeting. So all those technologies that we have been talking about today are basically come from the 3GPP family, which is third generation partnership project. So this is a global project which has members from different countries. So these are the different national level bodies from different countries. So from India, we have TSDSI, Telecommunication Standard Development Society of India. You have ATIS, that is from USA. The TTA is from this thing, South Korea. TTC is from Japan. ETSI is from Europe. I've given the names over here. So all these countries develop the mobile standards. Also, 3GPP has members from different companies. So people do come up with their technologies, have meetings, discuss, and finally this body decides, okay, for each layer, for each technology, what should be the network architecture, what should be the protocol, what should be the different elements, and so on. At the same time, mobile networks is not the only telecommunication method, right? So IEEE, I mean, it doesn't need any introduction to you guys. That is basically working on all these Ethernet and Wi-Fi technologies. So let's say ITU says that 5G means this. IEEE can also come up with something called their own, that okay, we'll have a Wi-Fi technology that is meeting your requirements. So when 4G came, 3GPP developed their LTE technology, and IEEE came up with their WiMAX. But somehow, due to performance reasons or international acceptance by companies and so on, LTE became more popular, and WiMAX did not pick up that much. So, but again, IEEE is basically providing you all the technologies. IETF is one body, International Engineering Task Force, that is basically developing your TCP/IP protocols. So this doesn't develop mobile protocols. This doesn't develop LAN protocols. It is only developing the protocols from network layer and transport layer. These things that you see. So there are IETF. This thing GSMA is basically a GSM alliance. So that is an alliance of all the mobile operators in the world. Open Mobile Alliance is another body that is defining standards for device management and so on. So these are different key bodies. There are hundreds of bodies. I mean, it was not possible to list everyone. So does this answer the question that somebody asked? What are the standard bodies that who frame this?
Yes, I need to take the snapshot of it. Yes, it's
I mean, you need not. I'll send this PPT to the coordinators, and then probably they will circulate it across.
okay.
So
Great.
I'll probably end this session now. In the next, so what I had prepared next was basically 5G. So what is 5G? It is basically a technology that is giving you at least 10 Gbps of speed. At the same time, the low technology version should, because as I said that 5G was designed not only for mobile technologies, but also for and literally anything that is there in the world, right? So if you are implementing it, implementing the technology for a smart meter or a IoT device, it should have a battery life of 10 years. That one charge of the battery should last for 10 years. Latency should be less than 1 milliseconds. The system capacity, it should be 10,000 times more than what was there in 5G, and so on. So this is basically your ultra reliability and high performance things, and all the things that we can see. Then there are two more things that probably you can study on your own. I'm just giving the names. One is V2X. So till now we have been talking about either mobile talking to the network, or we have been talking about smart like meters or fridges talking to the network. But now something is coming as V2X. So V2X means your vehicles are talking to the network. So your vehicles should be able to talk to each other. That is V2V. Should be able to talk to pedestrians. They should be able to talk to infrastructure and web services. So once your vehicle starts talking, it is more or less like a smart car, where you will have a hell lot of infotainment coming online. I mean, your instead of storing content on your pen drive or the internal memory, you will be able to download and watch stream movies in your car, not just on your phone. On the inbuilt infotainment system, V2X will basically provide you a lot of safety things. So in case there's an accident on the road that you're going, it will automatically instruct the car to slow down because there's an accident, say for example 500 meters ahead of you. So all those things will make your car smart. So V2X is basically one area where you can study and make a lot of applications about it. This is a typical example of where V2X is going to help you. And then Spectrum, I think MEC, I forgot to add the slide, or it was overwritten somehow. Anyways, so this is the last slide where I'm going to, this is the frequency thing that somebody asked. So this is the same electromagnetic spectrum that you studied in your class 12th. Different portions of this spectrum are used for different things. So the ones that you see in green are the ones that are used for mobile telecommunication. The red ones are, I mean, this portion is used for your TV communication, remote control toys, FM, and then satellite communication, radars, cable TV transmission, all this. So basically, it's the same frequency. Some components of it are used for different purposes. And then let's say, for example, this is a huge range of green. Now, in this range, mobile telecom standards are going to operate. But every country may not have this entire band free. It may be used by someone else. So either the country will allocate a portion of it, or it will basically not give this band. So I mean, alternate bands need to be used. So that, but the key idea is the mobile frequencies are no different from that used in television, satellite, toys, or something. The only thing is they are the same electromagnetic spectrum but different frequencies. So I think that's all. I know I went a little fast towards the end, but
Yeah, on this last slide, so there can be no overlap in frequency. I think
across the technologies, there should not be an overlap. Like a mobile frequency should not overlap with a satellite communication. Otherwise, it will be really difficult for systems to operate. So this is basically controlled by the governments and the telecom bodies. For example, in India, TRAI will make sure that I mean, the frequency spectrum given to military is different from mobile, and that is why all these auctions happen, right? In every country, you hear about auctions, right? So
yeah.
government first identifies that, okay, this is a spectrum that or this is a frequency that I'm going to give it to the mobile operators, and then it, let's say, for example, it decides that in this frequency I can only have 3 operators. Now there are 20 operators competing for it, so it has to sell, and then there's an auction happening that, okay, this is the price, whoever pays the highest will get it.
No, within national boundaries, that's okay. There is one body who's deciding it. I'm just saying that whether there can be a scenario that okay, that depends on probably on hierarchy of bandwidth. Like there is a communication happening from tower to a device or a mobile.
Yes. So even in this band,
Frequency.
when we say in this band, there are multiple sub channels or sub bands. So it's
Right.
not necessary that every country has to use all the bands. Some countries may be using band, say for example, let's say the bands are numbered 1 to 10. So some country may use all the 10, some country may only use 2 and 4, some country may only use 6 and 7, depending upon what is available in their country.
That's right. So I mean, it is possible that that an FM channel playing on 104 frequency, there can be a separate channel in US on the same frequency,
Very
right?
much, very much.
Okay.
Yeah, any more questions?
Like, can we use the same mobile phone in US?
As I said, there are multiple frequency bands. So if your phone supports the frequency band on which the US operator is operating, yes, you can use. If the, I mean, frequency is one of the criteria. I mean, there are multiple criteria. But now, since almost literally all phones are supporting all the frequency bands of 2G and 3G, that's why 2G is said to be a quad band phone. Right. So 2G and 3G definitely you can use, but a 4G phone of India may not necessarily support all the frequencies being used by the US.
Okay, thank you.
So for example, in India, we are typically using band 3, band 5, and band 40 for 4G services. But in US, they are using band 25, 26, band 13, band 41, band 3 and 5 are used, band 2 are used. So depending upon what bands they are operating and what bands your phone supports, right? So when you look into the network specifications of any phone, it will always list down what are the LTE bands that are supported. You can just go to GSM Arena website and then list down, I mean, select your model, it will give you what all bands are supported by your phone.
Okay, thank you.
I think in radar, satellite, or defense-related communications, it's more particular or specific for countries. As I mean, we try to build up some gateway communication, but that bandwidth which was I mean restricted from government. That that's
Yes, yes,
that
yeah.
frequency which is working commercially in France, it did not work in India.
Yes. So let's say, for example, the frequency given by Indian government to military may be different from the frequency given by the US government to US military.
Right.
But one thing is definite. For example, the TV broadcast band is over here, so no government can choose a band in 30 gigahertz and give it to TV broadcast, because TV broadcast technology is not going to work at that frequency. So it should be compatible. I mean, compatibility is also one of the key things.
Right.
So any other questions, or probably feedback that you have for this session? Did you like it? Did you not like it? Was it interesting? Did it meet your expectations, or it went typically?
No, it was great.
Especially students, how did you feel? Did you feel relevant? Were you able to catch on the topic, latch on to it? So yeah, Mas says it was informative. So there will be a feedback form that will be circulated. Do provide those, and uh, there will be a recording also. You can watch it later, as well as you can circulate it among your other classmates and batchmates, if you find it helpful. And for this was the sixth series of talks that we had for this session. So we'll probably stop for this session after this, and we'll probably see if we'll resume it in the next session.